My plan is to present to you some of the developments that I've been doing in Swansea for the last 5 years, 6 years approximately, in collaboration with a group of people, which are listed here. So one of them is Rogelio Ortegosa, who is a former PhD and postdoc, but now he's a fellow at the University of Cartagena in Spain. Emilio García Blanco, who is a former PhD student of mine, who is now working for a profitable company in Spain. Roman Poya, also a former PhD student of mine, who is now working at Siemens Industry Software for the development of mesh generation software for computational mechanics set in Cambridge. And finally, Professor Javier Bonet, who has been quite instrumental in collaboration, in providing ideas for some of the things that you are going to be seeing there. Needless to say, he was a PhD supervisor of mine, and probably he's the reason why I'm giving this talk in its origin. So apologies for the very long title of the talk, but my objective is really to talk about the use of mixed formulations in the case of finite elements for problems where potentially we can employ the concept of polyconvexity or multivariable convexity, as we used to call it, but now you can actually call it polyconvexity in general as well, as you will be seeing during the talk. Okay, so let me start quickly going through a brief outline of the talk. So I'll present first the motivation onto the two areas of interest of this work. One is in the area of hard mechanics, and the other one is in the area of electromechanics. Then I'll talk a little bit about mechanics, first principles, specifically trying to highlight the two areas that attracted our interest when we started with this research. One is on the complexity of the algebra that potentially features when we do nonlinear problems, and especially when dealing with the linearizations of the area and volume kinematic maps, particularly the first one. And then the possibility of using constitutive models, which in the case of reversible elasticity could be described by means of energies that are well posed, namely are going to be stable. So we were seeking for energies that were rank 1 convex, or in the case of having sufficient regularity, elliptic. I'll present them some of the key things that we have investigated in the area of hard mechanics and in the area of electromechanics, sorry. And then I will move on to examples in the case of hard mechanics, examples in the case of electromechanics. I got some videos, some movies that maybe I can share with you at the end of the presentation for the sake of time, and some concluding remarks that I will present to wrap up this work. So why did we decide to work on this area of hard mechanics? Because, well, it was obvious from the very beginning, the complexity of the subject, the challenge that it involved just to do it via experiments or via semi-analytical methods. We knew that modeling the heart was an extremely complex matter. And its interest in computational modeling is crucial because this gives a tool to help clinicians to diagnose better, to help clinicians to act more safely. Also the possibility to have a virtual environment where computationally you can experiment, whereas of course when you are in an operating theater you cannot do it. And also the possibility to have a better understanding of the heart motion and the heart mechanics and the different physics that are intertwined. We also knew that the correct numerical treatment of the problem was important, and that was one of the driving factors of this research. Here in this slide, what I summarize a bit in a nutshell is some of the physics that interact when dealing with hard mechanics problem. Namely, you've got the mechanical physics, which we have here in pink highlighted, which is the classical linear momentum conservation equation, which features here on the right-hand side, of course, in the case of very large strains and deformations. The second one is the electrical physics, namely the possibility of having a voltage diffusion throughout the tissue of the heart, which can be represented by this diffusion type equation, which, as you can see, depends not only on this diffusion tensor, okay, but also on these source terms, which it stems from the ionic modeling that is the third element of this puzzle. The third element is the chemical physics, the chemical part. As I said, ionic models, which are the ones triggering the motion of the heart at a given point, which are represented by a very complex and stiff set of ordinary differential equations, which can be as complex as one wishes. There is a variety of now well-established ionic models, some going from very, very complex modeling to other ones going to more simplified models. At the end of the day, it depends, as I said, on the set of ODEs, ordinary differential equations, that you want to solve. So there are some models that are particularly simple with very few ODE equations. There are other models where we have a very large set of ODEs that we have to solve in parallel. Of course, finding out the material parameters for that set of ionic model equations is extremely challenging, and it's still an open problem. In our case, what we were interested is not on this element of the research, not on that element of the research per se, but actually on the coupling of the three, and specifically on the possible limits that ionic models and voltage diffusion could impose on how can we describe the linear momentum equation, and specifically the stress tensor that features here, Piola, in the case of large strains, and how it could be coupled through voltage diffusion and through the ionic model. So that was one of the elements that, one of the examples that I'll be talking through in this presentation. The second one is the field of electromechanics, and specifically the area of application towards soft robotics. In a nutshell, I can tell you that, as you well know, probably robotics is now a hot area of research, has been for many years, possibly the last decade. But lately, a paradigm shift has been observed, and is that now researchers and applied scientists are actually trying to seek application of this robotics technology from hard robots to soft robots, and specifically what they're called artificial muscles. Okay, we are looking for materials that can be actuated by an electric field, but at the same time that can be very deformable. This is what they call artificial muscles, and some materials have already been identified as ticking the box, as being very deformable and electrically actuated. These are what they're called electroactive polymers. Within those, specifically the electroactive polymers. And within those, materials are extremely deformable, which will be the objective of their research, are dielectric elastomers, DE. As you can imagine, these materials are very attractive because they can potentially be programmable. So you can apply an electric field, they will deform. Then if you remove the electric field, they might return to an original configuration. There are, of course, some time-dependent effects, some viscoelastic effects, but in the context of this research, I'm going to focus on reversible elasticity. And these are some simulations that I've included here, some based on experiments and some based on in-house simulations that we've done with computer models developed within our group. Here to give you an idea of the challenge that this research involves, This is an experiment carried out in 2013 first, and then in 2016 in Harvard, and subsequently in the Max Planck Institute. And you can see a film made of one of these dielectric elastomers, which is subjected to an electric field across its thickness. As a result of that electric field, this dielectric elastomer film experiences an in-plane stretch, which is actually massive. You can see the change in shape from an original configuration to the current configuration, which is absolutely massive. Here in this diagram, I am plotting to you the stress diagram, which was recorded for some of these materials. And you can observe that we're talking of stretches prior to electrical breakdown, which can be in the value of 7 to 9, even larger than 9 for some of those materials. So these are values that are mind-blowing. I mean, they are extremely huge in terms of strains. And that means that everything we might know about linear elasticity, or even no linear elasticity, but in a moderate strain regime, they are not going to be particularly useful in this context. This is a simulation that we did in-house to illustrate this. And you can see it's quite interesting. It's sort of a helicoidal shaped shell made of one of these dielectric elastomers. We passed an electric field across. And then what we did is that we monitor the evolution of the area expansion with respect to the voltage that was applied. And you can see how the shape of the helicoid evolves. And particularly, I want you to pay attention to the size of the domain, because the size of all the helicoids is one-to-one with respect to the original configuration. Namely, this is the size approximately in the original configuration, and this is the size after the application of the electric potential. And you can see that the helicoid has increased its size dramatically. So I tend always to say that for me, these materials remind me of Alice in Wonderland. So Alice takes the potion, and then Alice becomes larger and larger and larger. And then ideally, well, potentially if Alice doesn't take the potion or takes a different potion, Alice goes back to her original configuration. So the change in size is actually quite dramatic. So some key concepts that I'd like to introduce regarding mechanics. I'll go relatively quickly. So the only thing that I will sketch for you is the classical potato diagram, as we call in continuum mechanics. So we have a potato in an original configuration, which we deform, subjected to a well-defined map. And this is the potato in the current configuration. So you can see that the size has changed dramatically, the orientation possibly as well, etc. And we can provide the mapping between the current configuration, capital X, the original configuration, capital X, and the current configuration, little x, is well established. Then you can define 3 maps. So the fiber map, F, the volume map, J, and the area map, H. And the typical way, at least in computational mechanics, to do so is that first we compute the gradient, from which we then compute the determinant, and then subsequently we compute the cofactor or the area map by multiplying the determinant with the transpose F of the deformation gradient. And if you've been involved in the area of nonlinear continuum mechanics, probably you've noticed that one of the most painful elements correspond to the computation of the linearizations of these maps that feature heavily when defining the constitutive models of these sort of materials. So one thing that we wanted was to try to simplify the algebra, and at the same time to drive, to get some insight that could be used. So how do we do this? Before I explain to you how do we simplify the algebra, one final key that is important to understand the motivation behind our research is the fact that we wanted to use constitutive models that were well posed, in the sense that ideally we would like them to be rank 1 convex. without going in detail, I want to show you an example of what basically that might imply. Okay, you can have a model, say a Semberan-Kirchhoff, and it is well known that this model, in the case of localized compression, does not behave very well. And this is what happens when we have a rubber-like made of this material column. Then we decide to twist it dramatically, as you can observe here. And then suddenly some sort of unphysical localized deformations start to develop here in this form of unphysical shear bands. Okay, this is what we observe. In fact, sorry. So how do we address these two issues? Namely, on the one hand, the complexity of the algebra, and on the other hand, the definition of well-posed models. So we've made use of a tensor cross product that, to the best of our knowledge, was put forward in the 1980s, and that we've used, we believe, for the first time in the context of continuum mechanics of cells, and we've used it in order to re-express the cofactor H in terms of that cross product, which is very, very handy. And then the determinant J can also be expressed in terms of this cross product. If you use these definitions, then the linearizations that I was mentioning to you before become then suddenly considerably simpler. Just to give you an example, the first directional derivative of the cofactor can simply be written like this, and the second okay, can you hear me now? Yeah. Yeah.
Yeah, now we hear you. Yeah, but there was some kind of a few moments where we haven't heard anything.
Did you get this the beginning of this slide, or should I go through it again?
I think the beginning was fine.
Okay, so I'll continue, but I'll rewind a few minutes. So as I said, we introduced this cross product, which we use to define the cofactor and the determinant, from where we get the linearizations. And for us, this was quite important, because if you can compare the first directional derivative of the cofactor with the classical first directional derivative that you can find in standard nonlinear continuum mechanics books, you can already notice the difference in the algebra. So compare this against this, and the difference is quite noticeable. If you go to the second directional derivative, well, it's even worse, because this is extremely simple in comparison with this, which I had to stop, because if you continue the dots, probably you can fill in the entire page out of linearizations. So this was one thing that for us was quite important, to simplify the algebra, and we felt that we achieved that. The second element was the use of constitutive models that were well posed. As we are going to focus mainly on hyperelasticity and its extensions into electrohyperelasticity, we decided to exploit the paradigm of polyconvexity. So polyconvexity was introduced in the 70s by John Ball, and from the computational point of view, it was possibly exploited for the first time, I believe, in the early 2000s by Schroeder and Neff and many others since then. And for those of you who are not aware, basically the internal energy of the system, the internal energy of this hyperelastic material, in the case of disregarding electrical fields, what it says polyconvexity is that it can be written as a function which is convex in these three arguments: F, the fiber map; H, the area map; and J, the determinant map. Okay. The beauty of this polyconvexity condition is that if you have polyconvexity in addition to further coercivity requirements, then you can guarantee the existence of minimizers. But from the point of view of stability, which is something quite important from the computational point of view, particularly when using Newton-based methods, what you notice also is that polyconvexity implies rank 1 convexity, and in the case of sufficient regularity, ellipticity of the model, which is what features here. So if we take the constitutive tensor and we pre-post multiply by rank 1 tensors, then what we end up obtaining is that polyconvexity implies that this product is going to be larger or equal than 0 for any A and for any N. And this is what ellipticity is. And this is basically what we observe in simulations. The moment that this indicator is not larger or equal than 0, that this localization indicator is not larger or equal than 0, then the finite element simulation starts to struggle, and then the results that we obtain are unphysical. So the question is, can we exploit this from a computational point of view further? Can we extend it to multiphysics? And at the same time, can we obtain an algebra which is, the algebraic derivations can be slightly simpler? That's what we wanted to look at. Okay, so quickly, we introduced these conjugate stresses, which are basically the partial derivatives of the internal energy with respect to these three strain measures that I mentioned before: F, H, and J, and we call them sigma F, sigma H, and sigma J. And what we did is we derived the principle of virtual work by exploiting these three conjugate stresses. So if we take the directional derivative of the internal energy, which is equal to the principle of virtual work in the case of pure reversible elasticity, and you apply the chain rule, which is what we do here, we obtain a closed form expression for the first Viola-Kirchhoff stress tensor, which features in the conservation of linear momentum. In terms of three stress measures, the conjugate stresses sigma F, sigma H, and sigma J, and the strain measures F and H. So this is a very nice expression that you can potentially exploit for implementation purposes. So for instance, in the case of a classical Munich-Riebling model with a given volumetric energy function, what we notice is that when we compute Piola directly by application of this formula, we obtain something like this, which is very nice, very neat, and very simple to implement. And you can see how the various ingredients, the various maps feature within Piola. So the fiber map, the coupling between the area map and the fiber map, and the coupling between the volumetric map and the area map. From the case of view of the tangent operator, which again, very useful for Newton-based methods. So this is the classical way the tangent operator would be obtained. But this is the constitutive tensor upon which we would love to have rank 1 convexity. If we use FH and J, as I mentioned before, then the tangent operator actually gets split into two terms. A first term, which is purely constitutive, and a second term, which is purely geometric, okay? And here the relevant operators are presented. The constitutive term has got in the middle this Hessian operator with respect to the three entries upon which the energy is expected to be convex, namely FH and J, which you can see here, that we know if we have an energy which is polyconvex, it's going to be positive definite or semi-positive definite. And this geometric term, very interestingly, in the case of considering rank 1 tensors for this gradient and that gradient, which is the requirement of rank 1 convexity, will drop, okay? And that's why we can say that we have done a very nice split between constitutive and geometric terms. Indeed, for the Munich-Rippling model presented before, this is the expression of the Hessian operator, which you can see that is going to be positive definite. And indeed, by substituting rank 1 convex, the geometric term drops, and then you get rank 1 convexity for free. So this is equal to this, and because this term we know is positive or equal to 0, then we have this guarantee. So that's the beauty of polyconvexity. Okay, now that we have these basic ingredients, let me show you how do we exploit this in the context of hard mechanics and in the context of electromechanics. Okay, so in the context of hard mechanics, in a nutshell, the equations that we're going to be solving from the mechanical point of view are the standard. So conservation of linear momentum subjected to, in the pseudostatic case, so it's equilibrium equation, subjected to appropriate tractions and displacement-based boundary conditions. Now, the complexity lies on the definition of P, Piola stress, which has to incorporate the heavily anisotropic behavior that hard tissue has, because it's hard tissue, and here is a representation, is a combination of collagen sheets and muscle fibers in a very complex anisotropic structure, which is also spatially dependent, okay? So the energy is typically defined like this. This has been done by several authors in the past. We have a decomposition of the energy into an isotropic contribution, you can see here, which is indeed a split into two components, a deviatoric and a volumetric. The hat on top of the F represents the deviatoric energy. And then it's got an anisotropic contribution, which depends on F, not on F hat, but only on F, and also on F0 and S0. F0 and S0 represent two of the directions of anisotropy that we are going to consider, which will be orthogonal in the original configuration. We don't need to consider the third, because the third is orthogonal to the other two, and then you can get one in terms of the other two. And a classical invariant-based energy that is typically used was introduced by Holzappel and Ogden, and by other authors subsequently, which is presented here. The isotropic contribution, I don't need to include it. It could be a Neo-Hookean type, a Munich-Rippling type, a Rudavois type, so many possibilities. Regarding the anisotropic, the typical way to do it is we have one term, okay? The energy, by the way, is always exponential type. So you can see an exponential here, an exponential here, and an exponential here, okay? And the exponent depends on this invariant, I for F0 square, I for S0 square, Okay, I'll focus on these two terms first and what do they represent. So I for F0 basically is this, is the stretch that takes place along the direction F0. The -1 is so that the energy is, well defined in the origin. And very interestingly, you can observe that it's got this Macaulay bracket. Okay, basically, we are only going to consider positive values. If there are negative values, they will be made 0. Okay, and then eventually this is a square. This Macaulay bracket is important because it guarantees ellipticity. If the Macaulay bracket is not present, then there is no way to guarantee that. The other term that can feature and presented by Holzapfel and Ogden is the invariant F0S0, okay, square, okay, which is defined like this, which basically, as you can see, represents the inner product between the fiber stretch in the current configuration. Now, unfortunately, this invariant, again, is not polyconvex because it's not elliptic, okay? And then this can potentially give you some trouble when doing simulations. So what we decided to do is to fix it. So we defined a polyconvex envelope for that. And the only thing that we do is basically this. So we replace this invariant with this other invariant, okay? So this invariant in terms of alpha and beta, which are two dimensionless material parameters, is such that it guarantees there is polyconvex, hence is going to be elliptic. So this is a very nice polyconvex regularization that we introduced. Now, from the point of view of the modeling, two typical approaches are established in hard mechanics. One is the active stress approach, and the other one is the active strain approach. In the active stress approach, Piola is obtained based on the classical energy coming from a hyperelastic model, plus a term depending on a scalar, in this case TA, for the case of a single fiber, which is driven by the ionic model that I presented at the very beginning of the presentation. So by changing TA, the stresses change. By changing F, the stresses change. The other approach is an active strain one. In this case, Piola is defined based on a given energy that depends on a deformation gradient F, which is obtained based on a multiplicative approach. So you need to know the real F coming from the kinematics, and you also need to know an F coming from an active strain stabilization, which is presented such as this. Depending on parameters gamma F, gamma S, and gamma M for the three fibers that again are ionically modeled. So, and these are the two approaches that feature in the literature. The definitions of gamma F, gamma S, and gamma M, and the definition of TA are non-trivial because they need to depend on the ionic models. And also you need to make sure that they are thermodynamically consistent. So authors have fought in order to achieve these objectives. This approach, the active stress, is considerably less non-linear than the active strain one, which is considerably more non-linear due to its multiplicative approach. So we implemented both, and we compared both like for like to see what we were getting. This slide is just to give you an idea whether the loss of ellipticity takes place in the model as presented by Holzapfel and Ogden. And what we see is that we took the invariant depending on this Macaulay bracket that I mentioned to you before, namely this one. And what we did is to deactivate this Macaulay bracket. So we let it work also in the compressive case. However, when you do that, this is what happens, is that sometimes the acoustic tensor gets ill-posed. It doesn't get well defined. You can see the strange representation that it takes. Whereas if the invariant is activated appropriately with this Macaulay bracket, you can see that now it's very well posed. the shape is very good. And then what happens is that as you refine meshes, you achieve convergence, which otherwise you don't for the first case. We also did some plots because these are representations for our within a material point, a Gauss point, from the point of view of finite element, a quadrature point. Here, what we did are contour plots of the loss of ellipticity and even the loss of polyconvexity by looking at the Hessian. So this was not that meaningful. What it is really meaningful is the first row. And you can indeed see that if the Macaulay bracket is not activated, you might lose some of the ellipticity of the model in some regions. Regarding the action potential, these ionic models, so what we do is a standard, but is not a trivial task. So this was the job of Emilio during the first year, to try to couple the ionic models with a diffusion propagation model, so that those two then are ready to be coupled to the mechanical part, which is what I described before. Oops, let me see if I can recover the slide. 1 second. I think the presentation is the slides are heavy, and there we go. Give me 1 second. See if I can get the slide back. Okay, I think I got it back. Give me 1 second. The slide is very heavy and is complaining at the moment, so I'm going to try to reopen the presentation to see if I can get the slide again. I don't want to, the computer doesn't want to show that slide at the moment. I might get it later on. At least I'm going to show you. I'll tell you what it was in that slide. Okay, so I cannot get it displayed here. I'm going to try to get it displayed here. Give me 1 second to see if I can close a few windows and get some memory back.
No problem. I mean, just take your time, and I think this can happen.
It's a very heavy presentation, and I had animation embedded, and Okay, now yes. Yeah, I had too many PDFs open. That's the problem of. So now I can share screen again. Okay. Can you see my screen?
Yes, we can.
Okay. So the last thing that I wanted to say regarding hard mechanics is that once I've shown you the three physics that we are going to couple, namely the ionic models, the propagation of this electric wave through diffusion models, and then the coupling into the mechanics through nonlinear elasticity using an anisotropic model, and the two approaches that we were going to compare, active stress and active strain. The last thing is very briefly sorry, now again, yeah. Now you can hear me.
Now we hear you, yeah. But
I think my computer is very greedy, and so is my microphone. So they basically take all the memory. But hopefully that doesn't happen anymore. I think I fixed it. So we used advanced finite element technologies, where we discretize not only for the displacements and for the electric potential, but also for the pressure, in case you're dealing with a tissue, like in this case, which is nearly incompressible. Or we could even go for other techniques where we discretize also for the deformation gradient F, the cofactor, the Jacobian, even the gradient of the electric potential. And then we look for Huesisu-Tai variational principles, and where we expect weak convergence, we leave the requirement of a strong convergence between the different fields, and that enables us to obtain mixed type variational elements, such as the ones that I'm presented here. Okay, the beauty of this is that you can get relatively high accuracy with coarse meshes in some cases, and enable us to assess what other authors had done in the past and observe how accurate you can get when you explore, for instance, hard mechanics in this case. So these are the sort of elements that we are looking at. From the point of view of electromechanics, which is the other field, so what are the main ingredients of the work that we've done? So this is the classical set of equations that generate from Maxwell, so Faraday and Gauss. These are the mechanics equations. And then, of course, what we look for is to couple both. So in the spirit or reversible electromechanics, we look for energies, coupling both the gradient of the mapping and the electric displacement, D0 in this case. And quite a few authors have contributed towards the definition of this sort of energies. And the typical approach is to have an energy additively split into a mechanical and electromechanical. As I said, many authors have contributed, providing energies. But one thing that got our interest several years ago was the possibility to ensure that these energies were well posed. And in the same way that polyconvexity had been used in the case of mechanics, if it was possible to obtain something similar in the case of electromechanics. Now, we were interested in the case of pure material stability, not in the case of existence of solutions at the time. So it's interesting because we worked towards the definition of an energy that could be like this, convex, not only in FHJ, like it would be in the case of a standard polyconvexity, but also convex in terms of the argument D0, the electric displacement, and D, which is sort of like a current, a special measure of the electric displacement D0. And what we observe is that when we were defining energies like this, they were indeed elliptic in the sense that we wanted. And for us, that was good enough for material stability. In parallel, Shilhavi proved that actually this definition, along with appropriate, again, coercivity conditions, is enough to guarantee the existence of minimizers. And that's what he called polyconvexity, extended polyconvexity. So we were calling it convex multivariable convexity, but it's the same idea of polyconvexity extended to the case of another physics. Sorry, with the microphone. So we look for conjugate stresses, one for F, one for H, one for J, but at the same time, one for D0 and one for D, as you can see here. And of course, our energy, in addition to be polyconvex, has to be objective or frame indifferent. So for sure, you need to guarantee this. Then we extended the concept that I presented for simple mechanics to the case of electromechanics. So the principle of virtual work now gets extended with this further contribution, and by applying chain rules exactly in the same manner. So an appropriate substitution, you obtain two definitions, one for Piola and one for the electric field. So Piola is like the work conjugate of your strain measures, and the electric field is going to be the work conjugate of your electric displacement. But in the case of this extended set of arguments, you can see how the coupling takes place. So it's very nice to observe how Piola couples mechanics with electrics, and how the electric field also couples electric with mechanics. Okay, so it's all coupled there. Here I just justify how we came up with the idea of the need to incorporate D as an extra field in the set of arguments, and is that if you don't include D, then the case of the vacuum, which is a degenerate case of our formulation, could not be embedded unless D was included in the set of arguments for polyconvexity, because the energy of the vacuum, which is presented here, is convex in JD, but is not convex in JFD0. Regarding the linearization, so this is how the linearization would be in the classical sense. You can see you got the constitutive tensor, but you also have further tensors, piezoelectric tensor and dielectric tensor. And these, in the case of an extended setting of all the variables that we've got, it looks like this, okay? So we have a pure constitutive term, and we have geometric terms. And these geometric terms become zero in the case of rank 1 convexity, okay? Hence, polyconvexity implies the rank 1 convexity even in the extended case of electromechanics. A classical case, so amonic rippling enhanced with electromechanic contributions. So one term, D0, D0, and another term, DD. And this is the way the conjugate stresses look for the definition of Piola. This is the way the Hessian operator would look like, potentially very ugly. However, for this particular material, everything is very simple, because only diagonal terms appear in the Hessian operator, and Piola and the electric field just can be obtained like this, which is remarkably simple. Regarding variational principles, so we are going to compare again, not just the standard displacement-based variational principle, but we're going to be looking at mixed variational principles. So I'm going to present to you probably the most generic one. This is the Hugo's isotype, depending not just on the displacements and the electric potential, but also all the extra variables featuring in the energy and their work conjugates. So basically we got FH and J, D0, D, and all of their work conjugates. Now, this variational principle from finite element point of view might sound crazy, but then using appropriate static condensation, then it's computationally as effective as a displacement based. So it's not that expensive after all. The beauty is that all the variational principles are possible because the moment that is a one-to-one relationship between this set of arguments and its work conjugate, you can potentially start applying Legendre transform at your will. So you can apply for some fields and not for other fields. So this is just an alternative variational principle, but there are actually infinite that are possible. And this is very interesting because of this one-to-one relationship. Okay. Otherwise, Legendre transform are not necessarily well defined, and then it's not that straightforward to define mixed variational principles, apart from the Hughes-Zissou type. Finite elements, again, we're going to be looking at interpolations for the different fields, standard nodal basis. There will be a Newton-Raphson, so we will have to invert a tangent operator as appropriate. And in the context of this research, we look at two formulations, one using mixed finite elements, using appropriate static condensation, and the other one using high order finite elements. So we were not looking for enhanced fields, but we're looking for a higher order interpolant for the displacement and potential. So just very quickly, some examples. So we were looking in the case of the heart. So we did first very simple test cases. So we took a beam made of this sophisticated and isotropic constitutive model. This is an example reported in literature. And we used different interpolants, and we were looking how the beam was deforming, and in particular for different features. And very quickly, you identify that the moment you have a very high aspect ratio, you're potentially going to need more elements across thickness. And that is something that is important to realize, because for some of the hard simulations available out there is not the case, and we wanted to make the community aware of that. We did the modeling of a ventricle, and we were comparing the different formulations, active stress, active strain, and also looking at monolithic approaches or staggered approaches. Namely, we were solving the mechanics, passing the information to the ionic model, and then coming back. And we obtained that results are fairly similar, provided that the staggered methodology is well implemented, and we have a sufficient number of time steps in order to do the staggering. We were monitoring a variety of fields, not just the potential, but also the deformations. Okay, we wanted to make sure that not only the potential was propagating well, but also the deformation of the ventricle was well captured. So this is something also that we looked at. And further results for the active strain and the active stress model. And yeah, some of the results that we obtained. We went as a specific to, depending on the formulation, whether it was monolithic or if it was staggered, we were listing how many time steps were required, how many subiterations for the staggering process were required. We wanted to be very, very specific. I got a hard simulation that I'll present at the end if I can. Regarding examples in electro, a variety of things that we did. So we've been looking at this sort of 8-shape behavior by placing electrodes in the right position. This was an isotropic model, and we were comparing different finite element solutions to demonstrate that they were locking free and so on. We also looked partially at a fiber reinforced actuator. We wanted to observe what we were obtaining, okay? And we noticed that indeed, depending on the orientation of the fiber, the way the actuator was deforming is dramatically different. And we were capable of getting very complex shapes, which is very interesting, because then that means that you can potentially tune the electric field and tune the orientation of the fibers in order to obtain tailor-made responses these sort of actuators. We also look at instabilities that potentially might develop within these components. This is the case of a half cylinder, okay, where electric field is passed across, and then of course the cylinder wants to expand dramatically, and then it develops buckling. Now, the buckling that you observe, the wrinkles that you observe here are physical, are geometrical instabilities, and we know they're physical because the model are polyconvex. So we wanted to make sure that the wrinkles that we observe here are due to the physics and not due to the ill-posedness of the model. We've also implemented this in high order and going for very, very large discretizations. This was with the help of Roman Poya. And then we've managed to do simulations that are impressive with many, many degrees of freedom across. And we were trying to model the onset of wrinkles. So these are some of the examples that we obtained for the case of a square shape flat plate, or for the case of a cylindrical, a circular, sorry. We were passing an electric field across and we were developing wrinkles, okay. Some conclusions. So basically the philosophy of the research underpinning what we did is, on the one hand, try to simplify the algebra. That's why this tensor cross product was quite important for us. And on the second aspect was the possibility to develop models that were well posed ab initio, which is what we try to do. Then, because I come from finite elements and my expertise is computational mechanics, so we wanted is to develop this mixed type finite element through a variety of variational principles. We looked for different Legendre transform types, and this is why Helmholtz type, enthalpy type, Gibbs type, or internal energy types energies are feasible in the context of this research due to this one-to-one relationship between strains and their conjugate stresses. The importance of using energies that are either convex, multivariable, or polyconvex, in the general sense. And from the point of view of the importance in hard mechanics, the importance of using energies that are well posed.
Antonio, we don't hear you.
Okay. Did you get again my microphone getting greedy? So the last few bullet points. So I don't know if you heard them. The importance of using well-posed models, particularly in hard mechanics, where we got the possibility to develop instabilities that are not physical. And then in the case of electromechanics, again, if you want to study the onset, the development of instabilities, how important it is to use models that are well posed as well, which was one of the things that we've tried to pursue with this research. And that's all. So I stop here, and I'm open for questions, or I can share some animations if you wish.
Yeah, so thank you very much, Antonio, for a very nice talk, which is now open for questions and discussion. So please, feel free to ask and pose questions. Maybe I may start. So you mentioned this rank 1 convexity, like that you search for models which the energy is rank 1 convex, but I just want to say that this is not enough, because rank 1 convexity still can give you, say, ill-posed models. So polyconvexity is the say better notion in this sense. Even so, I cannot give you really an example where I would have a rank 1 convex energy which is framed in invariant, and then And this is not like say quasi-convex. So this would be difficult. I mean, I'm not aware of any example in 3 dimensions at least, but yeah, in general we don't know.
Yeah. I mean, what we wanted was
I lost you again. I mean, we don't hear you. So if you hear us, we don't hear you.
okay. I can hear you now. Can you hear me now?
Yeah, I can hear you now.
So what we wanted was to avoid the possibility of doing a numerical simulation and then realizing that the wrinkles that we obtained were not physical wrinkles. So we said, okay, let's try first to try to set up energies that we think are going to behave well, and then we'll move on from there. The problem is that what we looked was energies that could behave well locally. So that's what we're looking, but and also helping the performance of the Newton algorithm. That's why we explore this.
Yeah. So
so if I may ask also, maybe just first comment on this rank 1 convexity, Martin, because I think it's quite standard in engineering community to consider rank 1 convex model because of wave propagation, right?
Yeah.
So I think this is one of the reasons why, like in engineering community, people are looking for rank 1 models, because they want to have a real wave speed.
Yes.
And then I have a question, because Antonio mentioned some geometric terms that they are 0 when you explore this rank 1 convexity.
Yeah.
Can you elaborate more on that? Because I don't fully understand. I remember also we discussed that because then it depends on a formulation you use, right? Because when you use, for example, second pillar Kirchhoff and green Lagrangian strain, you have some kind of geometric terms.
Yeah.
But when, for example, you use first pillar Kirchhoff and deformation gradient, you don't get any like geometric terms. Yeah.
Yeah.
So and in your formulation, you get like a different kind of geometric contribution to the stiffness matrix. So can you a little bit explain that in more detail?
I mean, when you do the linearization, see if I can share this slide. Put it here. So I'm gonna share screen and I share this. Okay. So the typical linearization, well, one of the possible linearizations is like this. Okay. This is very useful because it's extremely compact, and the only thing that you see is the constitutive tensor. From the implementation point of view, this is lovely. The problem is that this constitutive tensor hides everything. So hides both material and geometrical contributions. Other authors don't go for this approach. Other authors, they split, they carry out this linearization based on right Cauchy green tensor and the second Piola. And then again, they obtain in that case a constitutive term, and they obtain a geometric base term. Now, unfortunately, if you do that, when you want to consider the possibility of rank 1 convexity, so you test your constitutive tensor against gradients that are going to be rank 1 tensors, the geometric term doesn't disappear entirely. And the reason being is because the constitutive term has actually got also a little bit of geometrical term. However, if you go for a linearization based on FH and J, which is what you do here in the 3 arguments forming polyconvexity, then the geometric term is purely geometric in the sense that if we decide to substitute the gradient of delta V and the gradient of U with rank 1 tensors, this cross product immediately tells you that that term is going to be 0, because the cross product of rank 1 tensors is going to be, of 2 equal rank 1 tensors, is going to be 0. So the whole geometric term drops, and you only end up with this constitutive term. Now, because our energy we've said that is going to be polyconvex, if it is everything sufficiently regular, we know that this term is going to be larger or equal than 0, which is exactly what we would like to get. So any other kind of splitting into a constitutive and a geometric, the geometric is not going to disappear completely when you use rank 1 tensors. And of course, if you take it to the electromechanic case, then it goes even worse. So we found that this splitting was quite interesting, very beneficial at very quickly assessing if your energy happens to fulfill this requirement of rank 1 convexity. I don't know if I've managed to answer your question, Martin.
Yeah, so it's, for me, was completely clear. Yeah. So you consider geometric term that disappear a priori when you consider rank 1.
Correct.
Okay. And I have one more question. In one of the examples of wrinkles, you consider some special arc length method. Can you also comment on that?
Yeah, because to capturing this, we got different techniques. Because the problem is that when we want to do simulations beyond the onset of geometrical instabilities, then you need either a dynamic type modeling approach to be able to circumvent the overall instability that you're going to have in your Newton rhapsody. Or the option number 2 is to incorporate an arc length technique. So basically you introduce a parameter which is going to pre-multiply a nominal force term, and this parameter becomes one of the unknowns that you also solve. That way you can increase or decrease the load based on the requirements of the problem. This is a little bit more challenging here because not only you might have instabilities due to the mechanical part of the problem, but also you can have instabilities due to the electrical part of the problem. So it's not immediate.
Sorry, but we cannot hear you again now.
To sacrifice my microphone and go.
Now it's okay.
Let's go for the microphone of the computer. Can you hear me now?
Yeah, it's okay now.
Maybe the quality will be less, but that way it's not going to disconnect because I know that the microphone on my computer is less greedy than the other one that I've got here. So what we notice is that when you got simulations with many wrinkles, it's possibly better to have dynamics embedded and possibly with a viscous regularization term. That helps a lot. But if you've got problems where you got very few instabilities are going to be, then possibly you might be able to get away with an arc length technique. So what we did is to explore both for some of the simulations. So in some of the simulations, we were using one approach, and in other simulations, we were using another approach.
Okay.
Don't know if that's...
Yeah, but just one follow-up question, because I thought that when you use arc length, it somehow leads to non-symmetric stiffness, so you somehow lose this variational structure of the problem, no? So is there any comment about that?
Indeed. The moment that you use yes, but we also lose it in other aspects because I don't mind sacrificing that at that stage. Let me put it this way. Where can I lose symmetry? One is when you incorporate the arc length. Also, when you use finite elements that are not necessarily LBB compliant, and sometimes you want to circumvent by utilizing stabilization. The moment that you add a stabilization, you are also going to lose symmetry, which you don't mind sacrificing for the sake of robustness of the algorithm. Also, I've exploited also the possibility of structure preserving time integrators like energy momentum, and also we were losing the symmetry, of course, but for the sake of preserving very accurately the energy. Because this becomes very useful when, if you want programmable soft robots and you want the robot to run for a very long time, then looking at those sort of algorithms, energy preserving, that also is also a very interesting idea. So again, you don't mind at that stage sacrificing the symmetry. It's very difficult to have everything. From the computational point of view, it's very difficult, I would say.
Okay, I see. Thank you.
Yeah, so some further questions or remarks, comments, so it looks like it's not okay. So let's thank Antonio once more.
I don't know if you want to. I got here a couple of movies. I'm happy if you wish to share them with you. I don't know if you've seen them or not. They might be interesting.
No, yeah, maybe, yeah, why not? I mean, you can just.
So regarding the question of Martin, let me show you the one movie that we've got. I want to run it. Let me stop it here. I'll get it ready for you to see. I'm going to share screen this one. This is for the development of wrinkles. I don't know if you can see it. So we pass an electric field across and how the shell starts to deform and how the wrinkles start to develop. So here we've got the deformation of the component. Here we are monitoring the propagation of the, in this case, one of the metrics. So we're plotting pressure. And you can see that you get, very spectacular results. Because these are materials that potentially can deform a lot. So very quickly you get these massive deformations and wrinkles appearing. So this is one that I wanted to show you. Another one. This is a simulation of a set of ventricles that Emilio developed for his PhD defense. So hopefully you can see this. So this is a summary of the model that he was using for this simulation. This is the voltage as the ventricle deforms. You can see that you get very large deformations, potentially near, you can develop instability in some regions if you don't use models that are well posed, because as you can imagine, the application of boundary conditions here is quite complex. You need to have sufficient refinement across the thickness of the ventricle if you want to get meaningful results. And this is, for instance, one of the components of the ricocheting tensor, C11. And either you use very fine, a suitable fine mesh, or you use mixed finite elements in order to get the appropriate accuracy. One of the components of Cauchy. There we go. So there we go. Two examples of the sort of simulations that we were exploring during our research.
So maybe this, raise some questions or so. So if you have some question, please ask.
If you're shy but you want to send me an email and ask me questions, I'm sure you can find me. So don't hesitate.
So maybe I have one more question. In fact, yeah.
Go for it, Martin.
So were these simulations implicit or explicit?
The one that you've seen here The last one is, let me remember, the last one, implicit.
Okay.
This one was implicit. This one was absolutely crazy.
So do you have any, or do you remember how long it took to calculate something like that?
A week, approximately. I believe it took him a week. But the model was carefully designed. So if you see, the Poisson ratio was not chosen to, Emilio didn't go for a very large value of Poisson ratio to avoid having issues with, even though it was implicit, but having to reduce the time step a bit too much. And then we didn't go for a very sophisticated mixed formulation in this case. So the assembly of the stiffness metrics could happen very quickly. But I mean, some of the conclusions that we obtained when we were doing these simulations were incredible, because if you look at the literature on the sort of finite elements that are used to run these simulations, they are linear tetrahedra, and which, you know, in the case of near incompressible, we know that don't work. And we observed solutions where some authors were under-predicting the deflections that the ventricle might have. And hence that has got, of course, immediate consequences of the propagation of the electric potential. So these are some of the things that we noticed that for us were quite interesting to report.
Okay, thank you.
Yeah, so questions, last chance. It looks like there is no other question, so let's thank Antonio again for his very interesting talk. So
My pleasure.
yeah, and
thank you very much for inviting me.
Yeah, thanks a lot for the presentation, and hopefully we will see each other and next week at the seminar again. So thank you very much, and bye bye. See you next week.
Bye. See you. Take care.
Bye bye.